Everybody ready? Sorry. So we were looking at manipulating statistics the last class period. And when I say manipulating, I mean just manipulating in the sense that the way I show statistics or the way we talk about certain values or certain data sets can change the way that people perceive them. All right. And we talked about choosing central tendencies. Depending on which central tendency you choose, it can make the data set seem like it has bigger or smaller numbers. In this case, we saw that if you use the mean is, I forget, 80-something thousand. Whereas the median is 45,000. So if I use the mean to represent this data set, it's going to feel like, at least to a reader, that the salaries are higher compared to if I use the median to represent the data set. That'll make the salaries, again, in comparison, seem lower. Okay. And we talked about changing the subject. Changing the subject is where you use either raw numbers or percentages to make numbers sound bigger or smaller. By the way, using raw numbers or percentages is not the only way to change the subject. You can use other methods as well, but changing the subject means if you talk about it in one way, it makes the numbers sound big, but if you talk about it in another way, it makes the numbers sound small. All right. And we've looked at that as well. So today we're going to keep in that idea about manipulating the way people see and view a data set. And one of the most common ways of manipulating the ways people see data sets are by creating graphs that might have misleading features. So creating graphs that are more biased. Now, I'm not going to get into every single type of graph and every single thing that's going on, but let me give you at least a couple of examples of graphs that could be misleading. Let's say I took a bar graph and my bars looked something like this. And I'll give three options. We'll just call this option A, option B, option C. Now, if I look at a bar graph and it's written like this, B looks like it's at least, 4 or 5 times as big as A, right? Well, if it happened that my y-axis measurement started at like 75, and this was at 77, 79, I'll try to jump by 2s, 81, 83, something like that. This is a misleading graph. If I start this x-axis at 75 and it goes up to 83, very good job there. then the proportion of these bars to each other is not the same as the proportion of the numbers to each other. So if we're dealing with a bar graph, you want to start at 0 on the bottom so that the proportion, the size of the bar is in proportion to the size of the numbers. B looks like it's 5 times as big as A, when in reality, you know, it's 77 to 83. It's only just a little bit bigger. And if you redrew that bar graph with 0 at the bottom, it would probably look, I don't know, more like this, which gives you a very different type of impression, right? This happens a lot in certain advertising. If I am the person who is marketing for product B, let's say these are 3 competing products, and I say, well, look at how people graded each of these products. Like they graded this one at an 83. Putting a graph like this makes it look like there's a big difference. Putting the graph like this means, or makes it look like there's not much difference at all. Everybody follow that? So a lot of times people will do that with bar graphs, and you have to watch out for bar graphs that don't start at 0, because then the bars aren't going to be proportional to the numbers that they represent. Okay. Now, another type of misleading graph is one where we may look at how some sort of quantity changes over time. And anytime you're recording a change over time, the time frame that you choose matters. Different snippets of time can give your graph very different looks. Imagine the thing that I just drew. If I gave you a snippet of time from here to there, it looks like the change is going down. If I give you a snippet of time here, well, it looks like it went up and then slightly down, and you get a bigger picture. Anytime you're looking at change over time, the time frame covered can make a big difference in the appearance. All right. Let me give you an example of that. So something that's very common to keep track of as far as change over time is the stock price. All right. So here's some different stock prices. Let's click on Meta. This is the Facebook parent company. You guys know that? Called Meta. Well, if I choose the 5-year version of Meta, like the 5-year financial past of Meta, you can see that kind of went up, went down, went up, went down, and then it went really up, and then went really back down, right? And it's almost the same as where it was in 2018, 2019, 2020 right now. Okay. Obviously, if I clipped this at July of 2021, or if I just went from here to here, looks like the stock is growing. But what if I would have went over a 1-year period? Or maybe I would have went over, this. So I take this time frame, which is a little bit over a year, and you can see that in this time frame, it looks like Meta stock has really tumbled. And it has over a year. Bear with that. And so if I were trying to convince you to not buy Meta stock, maybe I'd show you this picture. However, if I wanted to try to convince you to buy Meta stock, maybe I give you this picture. Right? The over the last few months picture. Over the last few months, Meta stock, started out at just over 100 and now is at 174. That makes sense. So time periods matter. If I started at November the 3rd, then it was right at like about 90. Now it's at 174. So time periods matter when you're talking about tracking quantities over time. Which time period do you give? And that's always important when you're looking at a graph where the X value is your time period. You should always ask, well, why did they choose that time period? Why did they choose that particular time period? Now, the last way about manipulating statistics is just subtle difference in how you measure things. Subtle differences in how you measure things. And how you measure something is called a metric. So a subtle difference in the metric, how you measure something. A metric is essentially kind of like a ruler. So if I'm looking at income in the United States, I could measure income per individual like per person, or I could measure it per household. And those would give you different numbers. Because if you think about per individual versus per household, my mom is an individual and a household, so her income counts as the same both ways, right? But in my household, my wife and I live in my household. So if you counted per individual, we'd have 2 incomes, but per household, we'd have 1 income. And that number would be, bigger because our 2 incomes would be added. Everybody follow that? So per household income versus per individual income would give you different measurements. And one of those might be larger than the other. The household usually is larger than the per individual. Now, this is kind of similar to changing the subject. You're talking about incomes in 2 different ways, but it's different. Changing the subject is you're not talking about money values, you're talking about percentages versus raw numbers. Does that make sense? Or something like that. Here, we're just talking about how did you measure something. Also, life expectancy. If you look up life expectancy, oftentimes life expectancy is calculated differently based on what country you live in. In America, when an infant dies at birth, we count that as a person who lived 0 years. Does that make sense? In some countries, when an infant dies at birth, they don't count that at all. They don't count that as a person who has lived. And so the numbers are going to be different. The numbers are going to mean different things. Life expectancy, which counts infants as living 0 years, versus life expectancy where infants who die at birth are not even put into the calculation. All right. And then a very famous examples are like healthcare rankings. Anytime you're ranking something, whether it be healthcare or favorite music artists or anything like that, you always have to ask, well, how was this done? What are they actually measuring healthcare rankings on? Are they measuring healthcare rankings on people who survived breast cancer? The US has like the best cancer survival rates once it's detected. Or are they ranking it based on cost? Well, the US has one of the most expensive healthcare systems in the world, right? And some of the reasons for being most expensive is because we're one of the healthcare systems which treats a lot of these rare things, which cost lots of money. Where in other places, oftentimes they say, hey, your survivability on this thing is only like 1%, so we're not gonna spend the money on that 1% chance. Does that make sense? So. So we have really good survivability ratings, but we also have really high costs. And so if rankings talking about survivability ratings, survivability of cancer, the US is really good. You're talking about affordability, the US is really bad at that. So there you go. Any questions about that section? How to present data and how data can be misleading, right? Choosing different central tendencies, the mean, the median, the mode, changing the subject, using percentages versus raw numbers, graphs, we saw a couple of those. You can mislead by choosing certain time frames, and then using different types of measurements which sound similar but give different results. All of those are ways to manipulate the way people see statistics. Now, lastly, in the statistics chapter, we're going to talk briefly about understanding results. And the big idea here is that whenever we see statistics, we need to understand that when we're talking about statistics like central tendencies of a data set, we're looking at the data set as a whole and not every individual in that data set. Now, if you are looking at a single individual, that's known as an anecdote. Anecdotes are just single individuals or single individual stories. And using anecdotes to justify a claim is a common logical fallacy. All right. When you want to understand general trends, you should not use anecdotes. When you're trying to understand general trends, you want to use data from general population rather than using anecdotes. All right. And the reason we want to do that is because often, well, most likely, if we're using data, it has the ability to be replicated and patterns can be established rather than using anecdotes. All right. Now, I'm going to give you some statements that we want to understand, okay? And this is about understanding that statistics looks at the group, not the individual, all right? There have been studies that show that people who smoke are more likely to commit crimes. Smoke cigarettes here. Now, what is that saying? And what is it not saying? Well, that's saying if you look at the group of people who smoke, they have a higher crime rate than the group of people who do not smoke, right? So we're saying the group who smokes has higher crime rate. All right. Obviously, that's compared to the group who doesn't smoke. Now, I already know what you're thinking, because we've been trained to look at statements that way and say, well, I know somebody who smoked. My grandmother smoked, and she was not committing crimes, right? So when we see a statement like that, we also have to understand that we are not saying everyone who smokes commits crimes. We're also not saying that if you're a non-smoker, you're not going to commit crimes. There's lots of non-smokers who commit crimes. We're just saying that there's differences in the rates. Now, furthermore, are we saying that the differences in the rates are because of the smoking? We're not saying that either, right? We're just observing. We're not saying also crimes happen because of smoking. Back that. So we're saying that there's a difference in the rates, and that smokers have a higher rate than non-smokers. But we're obviously not saying that that statement applies to every smoker and every non-smoker. And those differences in rates may or may not be caused because of the act of smoking. Probably not in this case. Probably not in this case. You know, I think I mentioned this earlier. Maybe I mentioned this in my other class, but a lot of times you just see higher rates of smoking in lower income communities, and lower income communities are also associated with higher crime rates. So that's what that is. So again, we should understand when a headline comes across and they say, well, there's been a new study and they found that people who smoke are more likely to commit crimes. You say, okay, so there's a difference in the proportion who commit crimes in smokers and non-smokers. And you should really be careful about headlines. People who publish headlines like these aren't really doing a service to themselves or to the general public, because there's almost an air of causality that the headline implies, but that is not the case statistically. Statistically, it's probably not the smoking that's causing the crime rates in those communities. All right. And this is a problem with a lot of studies, because a lot of studies, once they're done, they'll look at two groups and compare them, and they'll say, well, this trait, crime rates, is more likely in this group versus the other group. And then those studies will be published. And people will interpret those studies as some sort of a direct cause. Okay. And this is very common in like healthcare. You'll see these studies that get reported in the news that say you're more likely to have a disease if you do certain actions, like eat certain types of foods, or you carry a certain gene. Therefore, you're more likely to have such and such disease. And that may be true. You may be more likely to have such and such a disease, but we don't know if that action or if that eating of a certain food or carrying of a certain gene is actually the direct cause of disease. Does that make sense? All right. Okay. Now, another type of statement that you can see in statistics is something like this: smoking causes lung cancer. All right. Now, again, this is kind of like the previous one. If you see a headline that says smoking causes lung cancer, it again means that the group who smokes has higher lung cancer rates compared to non-smoking groups. It is not saying that everyone who smokes gets lung cancer. Now, and this one is in this case, as opposed to the previous case, as opposed to committing crimes, with the committing crimes, there wasn't probably a direct relationship between smoking and committing crimes, right? It was more likely that, you know, it was this other fact that both happen in low-income communities at higher rates. In this, there probably is a direct causational relationship between the smoking and the lung cancer, right? You put a lot of smoke and black stuff in your lungs, and you're more likely to get lung cancer. Does that make sense? So in this case, it is probably more of a direct causational relationship, where in the previous case, it wasn't so much. It was more of an indirect relationship. Does that make sense? So understanding these headlines is fairly important. Okay. By the way, people have done lots and lots of studies about genetic markers that are indicators of getting certain diseases. Okay, it's very much like bigger proportion. It's not always 100% of these people have the disease and 0% don't. A lot of times, even with these genetic stuff, which you might think, well, man, that's got to be a direct cause. It's actually a little bit more complicated than that. And it's even then, it's higher likelihood. So everybody get that? So if you get a result that says something is more likely or something causes this, don't automatically think that that applies to every single individual in the group. Okay. And to piggyback on that, often there are studies that say one group has higher average than the other. Group A on average is taller than group B. Or group A commits crimes at a higher average rate than group B. Okay. Some people say, well, why would you ever want to compare groups like that? And why would we ever care about which group is higher, lower than the other? Well, we care if you want to try to, fix problems in society, okay? And allocate resources to the right places to help fix problems. Sometimes when you look at group A has a higher average than group B, if it's a trait that we associate with being a positive trait, a lot of times people will say, well, then group A is better than group B. But that's not really the case. Just because one group has a higher average on something doesn't mean that group is better or worse than the other. And just like our smoking and committing crimes, we can't necessarily attribute some sort of unfair circumstances to group A versus group B. All right. So it doesn't make one group better, and it doesn't, just the fact that averages are different doesn't prove unfairness. Okay. So let's talk about income for a second. Average income of males is higher than the average income of females. All right. So let's go through this. Why would we care? Well, we would care because that has implications throughout society on resource allocations and all that kind of stuff. Does this mean that males are better on average than females, or females are better? Of course not. Doesn't mean males are better than females or females are better than males. right? Just if you see a statement like that, does this mean that there's some sort of an unfairness in the workplace for females? Well, not by this statement alone. There could be a lot of reasons for this type of statement. And to be blunt about it, there are. Males and females on average work different types of jobs. All right. The number of female elementary school teachers is high compared to male elementary school teachers. And the number of males who work on deep sea fishing boats is high compared to females who work on deep sea fishing boats. Those differences in occupations might cause at least the vast majority of the average income difference. All right, does that make sense? So it also doesn't necessarily mean some unfairness. Now, there may be some unfairness in workplaces. I'm not saying that there's zero unfairness in workplaces. What I'm saying is this statement doesn't tell you that. All right? You're going to have to dig into some of the other causes, like those lurking variables, and say, well, what are those lurking variables? One of them is what I just talked about, job selection between males and females. On average, males and females select different types of jobs, working on deep sea fishing boats versus working in elementary schools, right? So then there's others as well. Time that you've been in one job and all that kind of good stuff. So I'm not saying that there's no unfairness out there. I'm just saying that that statement doesn't prove unfairness. Everybody follow that? All right. Here's another example of that same phenomenon. If you said in America, the height of Black Americans is greater, the average height of Black Americans is greater than the average height of Asian Americans. That's a true statement. You can look up the numbers in the CDC. Same thing with the income. That's a true statement. You can look up the numbers and it's CDC, the Census Bureau. Census Bureau gives you that stuff. This statement doesn't mean that Black Americans are better than Asian Americans or vice versa, right? And it's not proof of some sort of unfairness. That's just a statement of fact. Does that make sense? So this is all about understanding results. This section was all about understanding results, understanding the difference between more likely to happen versus direct cause. Understanding that when we're given statistics, we're talking about groups and not individuals. This doesn't mean that all Black Americans are tall and all Asian Americans are short, right? There's Black Americans and Asian Americans of all heights and shapes and sizes. All right. So we're not saying that all females have low incomes and all males have high incomes. Right? We're saying that the average of the group is different. Doesn't mean that one group is better than the other. And that's not necessarily evidence of unfairness. You have to look a little bit deeper into the causational reasons if you want to show unfairness. All right. Now, the last thing I'm going to do in chapter 3 is talk briefly about doing some statistics in Excel, doing some calculations using Excel. Now, if you have a Microsoft Office or a computer that's running Microsoft Office, then you have Excel. And that's one of the more common platforms, is the Microsoft platform. So we're going to use Excel. It is obviously not the only computer program that will do statistics. And the reason I want to show you this is that in reality, when people do statistics, they do not do them by hand very often. It's good to do statistics by hand on some small cases so you understand what's going on. But when you get into really big data sets, everything is done by computers. So again, there's lots of different computer programs that can do the same thing. We're going to use Excel because, well, it's free and it's not free on most, it's already put on most computers, okay? And I think all of the college's computers have Excel on it, all right? There's also an Excel, an Apple version of it too, so. So remember this data set where we had heights of buildings and we found the average and the median. So we found the mean, the median, we found the mode, there was no mode here. We didn't find the standard deviation or the range, but that's fine. Let me show you a way to deal with this in Excel. So first off, if you're dealing with Microsoft, you just hit the little window key, and then you go to Excel, click on that. We'll go a blank workbook. Excel has all these rows and columns. Rows are numbered, columns have letters. Okay. What I'm going to do is I'm just going to copy and paste those data probably shouldn't be that big. So copy and paste the data. Yeah, we'll do this too. See if I can go a little bit. Oh, 18, that's better. There we go. And there. Now there's a lot of things I can do in Excel. Everybody see that? Read that fine? I'm going to show you a few formulas. So if you go into formulas, auto sum, there's your average. Notice that if I click on equal average in the thing, in the block that I'm dealing with, it just says equals average, and then parentheses. So I need to tell it what average to take. I want it to take the average of these numbers. I can just click my mouse and carry that and highlight all those numbers. And so this says equal average B2 colon B7. So this is averaging the numbers in all the way from B2, that's column B, row 2, all the way to B7, column B, row 7. And then I hit enter. And I get 2100. Now let me make that a little bit bigger. Make it the same size. So that's how you do a mean. So the mean is 2100. Is that what we got last time? Everybody remember that? Should be. Now let's look at the median. Now you can either keep looking up in the formulas. So you just go to the formulas and then you try to look for a function. Sometimes median. There you go. Median. If you don't want to go to the formulas, then a lot of times you can just go equals median. And then in parentheses, the numbers I want to find the median of. Hit enter. 2016. Okay. You could do the same thing with mode as well. So this mode, singular, returns the most frequently occurring. Oh. Highlight. Notice it says NA. Why do you think it says NA? That just means it's not available. And therefore there's no mode, right? There's no mode if it's not available. You can do the same thing with the range. Just go equals range. I think it's range. Oh, I hit the wrong one then. Range. Distance. Oh, where is, so let's do this. Let's look it up. Range. All right. Count to count. Yeah, I don't have a range here, at least not one that I see. There is a maximum though, and minimum. So I guess instead of doing a range, what I could do is say equal to the maximum of these numbers minus the minimum of those numbers. There you go, there's my range. maximum value minus minimum value. And then let's look at the population standard deviation. Now the standard deviation for the population is STDEV dot P. This is the standard deviation. I just highlight those numbers. And there you go. Standard deviation is 288 point, essentially 0.1. Is that nice? So if you know those formulas, if you know what to type in Excel, our measures of central tendency and our spread measures can be calculated for us. Okay. Another thing that you could do is you could also, if you'd like, insert some graph. There's a graph, a bar graph of the different heights of those towers, right? Notice that in this case, my bar graph started at 0 on the y-axis. And that's what I wanted to do so as not to be misleading. Is that right? So in order to get the mean, what we did is we wrote equal average and then highlighted the numbers we wanted to average. To get to the median, we wrote equals median and then highlighted the numbers we wanted to find the median of. The mode is equal to mode dot SNGL, that's single. And then highlight the numbers. The range, maximum of the numbers minus the minimum of the numbers. And then the standard deviation, we use the population standard deviation. So it's STDV dot P of those numbers. They're pretty nice. Now, if you're ever given a really big data set, you can calculate those things that we calculated at the beginning of this chapter in a fairly efficient way. All right, so we did that. Built bar graphs of the height. Does that make sense? You can do all that stuff as well with this data set. I think I'm going to skip this data set since we all don't have computers on us right now. I'll just show you that one example. Is that right?
We're gonna have to use Excel and
Nope. You don't have to. And the Excel part is the bonus homework. Okay. And so we all know what that means. That means you can do it if you want. If you don't want, you don't have to. It's not going to count against you. But if you do it, you do it really well, it counts for you. And on the test, that bonus homework, there'll be no bonus homework type problems on the test. That's what these stats in Excel is. All right, everybody good with that? Stats in Excel stuff. So then today, I'm going to start in dealing with chapter 4. Chapter 4 is about probability. say probability, probability means the chance that something occurs. The chance that some event occurs. So it's the chance that if I roll a die, it lands on the number 4. The chance that if I flip a coin, it lands on heads. The chance that as I drive home today, I get in a car accident. The chance that the Kansas City Chiefs repeat as Super Bowl champs next year. All right. Now, in each one of those situations, there is an underlying process that's happening. That underlying process that's happening is the probability experiment. The probability experiment is the process, the chance process that leads to well-defined results called outcomes. So if I'm talking about rolling a die, the act of rolling the die is the probability experiment. And I'm going to be asking what's the chance that the die lands on the number 4. The flipping of the coin is the probability experiment. And I'm going to ask what's the chance that the coin flip lands on heads. What's the chance I get in a car wreck on my way home? The probability experiment there is me driving home. And either I get in a wreck or I don't. Or we talk about Kansas City Chiefs winning the Super Bowl next year. Well, next season's NFL season is the process, right? That leads to those results. The result is who wins the Super Bowl. Okay. Now, when we're dealing with probability, probability is always going to be a number between 0 and 1. 0 means that the thing can't happen. Like, what's the chance that my kid's Little League team wins the Super Bowl next year? You'd say there's 0 chance of that happening because their team is not in the NFL. Okay. What's the chance that the Super Bowl champion next year is a team from the US? Say, well, that's probability of that happening is 1 because all football, right, NFL teams are based in the US. So it has to happen that way. And in order that we don't have to write the word probability of this happening out over and over and over, we use special notation where we write a capital P and then in parentheses of the event. That means probability of the event happening is equal to whatever the number is. So P in parentheses, whatever event, just means probability of the event occurring. Is that okay? That's pretty straightforward. Unclick it. So probability of the event occurring is capital P and then in parentheses E. That number is always going to be between 0 and 1. A lot of times we're going to write that as fraction. A lot of times we'll write that as a decimal. Okay. So in this chapter, the goal is going to be twofold. One, we're going to look at some basic probability calculation rules. All right. And then two, we're going to see how probability can be used in everyday life, specifically how it applies to insurance problems and how it applies to problems with chance and choice. Okay. So there's a lot of different probability uses in everyday life. By the way, all of us do this informally. We use probabilities all the time. Like the fact that we feel comfortable driving to the grocery store and we don't think anything of it. I talked about me driving home today. What's the chance of me getting in a car wreck? I don't know the exact number, but it's pretty low. So I feel pretty comfortable driving home today. I could have reduced my risk driving home today if I would have had a car instead of having my car. If I'd have drove home in a M1 Abrams tank, right? It'd have been a lot safer. Then anybody who hits me, I'm perfectly fine inside. You know what I'm saying? But I ended up having this normal sized car because my gain of safety from the M1 tank is not that big of a deal, right? It's a low probability I get hit, and even if I get hit, it's a low probability that that something really, really bad happens to. Okay. That makes sense? So we all use these probabilities informally in everyday life, but we're going to more formalize that here. All right. The same thing, maybe the driving home and getting in a car accident isn't as real to some people. So let's do another example. As you're driving, most of us feel fairly comfortable driving a couple miles over the speed limit, right? That's really a probability type decision. It's an informal probability decision. I feel comfortable driving a couple miles over the speed limit because most police officers aren't going to pull you over if you're only going 3 miles an hour over the speed limit. And during any small section, stretch of road, 3 miles in speed, you're unlikely to see a police officer in the first place. Does that make sense? So the probability of seeing a police officer, and then on top of that, the probability of that police officer giving you a ticket makes it a very, very low chance that you would get a ticket for going 3 miles an hour over the speed limit. Does that make sense? So there you go. So we all use informal probabilities, and we will use formal probabilities in this class. Now, instead of starting a new section, because the new section will take a few minutes, so we're not gonna do that. We'll start that 4.1 section next time. Now we know what probabilities are. We'll start calculating those probabilities next time. And I'll show you a couple different ways to calculate probabilities and a couple of different tools. All right. Don't forget, in terms of what's due, the homeworks for chapter 3, 3.2, 3.3, and also 3.4 through 3.6 are due Friday. The bonus homework, that also, yeah, that's also due Friday at 5 too. So if you want to do any of the homeworks for chapter 3, the statistics homeworks, obviously the 3.0, 3.1, that was due last week, but the other 3 homeworks are due this week. Okay. All right. Well, I will see you all next week.